Hello everyone. My name is Minh, and the title of my talk is Impossibilities of Precise and Sound Termination-Sensitive Security Enforcement. So before introducing the main results of our paper, the impossibility results, I will just present termination-sensitive non-interference, secure multi-execution, and a problem about secure multi-execution. So first, in order to present termination-sensitive non-interference, so I will to give just a brief description about programmed. So we consider deterministic imperative programmed with input and output operation. So here is an example of such a program. So input H from CH and YH larger than 0, then do skip. So the basic idea of this program is that, so basically the execution of this program will consume an input value from the input channel CH, and then store this input value to the variable H. And after that, if the consumed value is larger than 0, then the execution will enter an infinite loop. So for deterministic imperative programmed, then a state is a pair with two elements. The first element is a state P, and the second element is a memory Mi. And we write terminating P, Mi, and I to mean that the execution of the state P and Mi with the input I terminate. So for example, with the example, notice that this example will be used throughout the talk. So with the input I, with the input value 0 from the input channel CH, there and the memory Mi, then we have that this execution, the execution of the program P will consume the value 0 from the input channel CH, and it's does not enter the infinite loop. So that's why the execution of the state on this input terminate. Okay, so now we look at termination-sensitive non-interference. So for the purpose of the talk, I just have two security level, L for the public information and H for the confidential information. And we write I equal L, I1 to mean that I1 and I2, the input I1 and I2 are equivalent at the low level. So now we have the definition of TS and I. So we say that a state P and Mi is satisfy TS and I if for all input I1 and I2, then if I1 and I2 are equivalent at the low level, and the execution of the state on input I1 terminate, then we require that the execution of the state on input I2 also terminate. And we have another other conditions. And the other conditions are not important for the talk, so I will not give the further explanation here. So one important observation from the definition is that TSNI state either converges on all input equivalent at L or diverges on all input equivalent at L. So here is an example of a state that does not satisfy TSNI. So we consider the state P and Mi, where P is the program already presented before, and Mi is memory. So and we suppose that we say that CH is a confidential input channel. It means that all input values from this channel are considered as confidential. So we first consider the input I1 with the input value 0 from the input channel CH. Then on this input, the execution of the state will consume value 0 and then it's terminate. For the input I2 with the input value 1 from the input channel CH, then the execution consumes the value 1 from the input channel CH. And because this value is larger than 0, and then the execution enter an infinite loop, and therefore the execution does not terminate. So we have that I1 and I2 are equivalent at the low level because they have only confidential input values from confidential input channel. But the execution on the first input I1 terminate, but the second execution on input I2 does not terminate. So that's why this state does not satisfy TS and I. Okay, so now we look at secure multi-execution SME. Introduced in SP 2010, and this enforcement mechanism was proven to be able to enforce termination-sensitive non-interference. So for secure multi-execution, the basic idea is multiple local execution. So that means that to enforce termination-sensitive non-interference for defined on any arbitrary finite lattice, then secure multi-execution will run several copies of the original state, each corresponding to a level in the lattice. And the second feature of the secure multi-execution, the version introduced in 2010, is a low prior scheduler. This scheduler is about the order of executing local execution. So here is an example of SME with two security level L and H and with the state P and V. So with this setting, then we have two local execution called the high execution and the low execution, each corresponding to a level in the lattice. And the high for the low prior scheduler, then the high execution is executed only when the low execution terminates. And for the low execution, then when it needs input values from a public input channel, then yes, it can consume an input values. And when it needs an input values from a confidential input channel, then it will use default values. And the low execution is the only execution that can send output values to public output channel. And its output values to confidential output channel are suppressed. For the high execution, then when it needs an input values from public input channel, then it has to reuse the input values consumed already by the low execution. And this is the execution that can consume input value from confidential input channel. And this is the only execution that can send output values to confidential output channel. Okay, so in this slide, I will illustrate the SME by executing SME on the state P and V presented before, and notice that this state does not satisfy the S and I. So, so suppose that the default values for CH is 0. So now we look at the execution of SME with the input I1 with the input value 0. So we have that for this execution. The low execution will, when it needs an input value from the confidential input channel CH, then it's used a default value which is 0. And that's why this execution does not enter the infinite loop and it's terminated. For the high execution, it's consumed the actual value from the input channel CH, which is 0, and hence it's also terminated. So because both local execution terminate, so therefore SME also terminate. Okay, so now we look at the formal properties of secure multi-execution. So secure multi-execution were with a low prior scheduler was proven to be sound and precise with respect to TS and I. So to be sound to me, it means that SME with any state P and V satisfy TS and I. And precision is mean that if a state P and V already satisfy TS and I, then SME will not change the original behavior. So, but the problem is that SME with a low prior scheduler actually does not enforce soundly TS and I. And I will illustrate this problem via an example. So this is, so in this example, we will execute SME again on the state P and V, where P is the program, input H from CH and YH larger than 0, then do skip. And CH, notice that CH is a confidential input channel, and the default value for CH is 0. So on input I1, with the input values 0 from the input channel CH, then as explained in the previous example, then the execution of SME terminates. On the second input, with the input value 1 from the input channel CH, then the execution of SME does not terminate, because with this input, the high execution will consume the actual value from the input channel, which is 1, and hence is enter an infinite loop. And because the high execution diverges, so the whole SME is also diverges. So we have that I1 and I2 are equivalent at the low level, but the termination behaviors of SME on I1 and I2 are different. So on I1, SME terminate, but on I2, SME does not terminate. So SME does not enforce soundly TS and I. So at this point, there are two research questions naturally arising. The first question is there any sound and precise enforcement mechanism for TS and I? And notice that if we do not care about the precision of an enforcement mechanism, then we do have enforcement mechanism for TS and I. The problem is that such an enforcement mechanism may be not so useful or may be conservative. And so therefore, we require that an enforcement mechanism has to be sound and precise. And therefore, the first research question is there any sound and precise enforcement mechanism for TSNI? And the second research question is, so which policies is actually enforced soundly and precisely by secure multi-execution? Okay, so now we look at the first research question. Is there any sound and precise enforcement mechanism for TSNI? So to answer this question, so we first to have a definition of enforcement mechanism. So an enforcement mechanism, EM, of a policy P is a total and recursive function from state to state. So because it's the total function, so that means it can be applied to any state. And because it's recursive, so that means on any state, the function will return a state in finite time. And we say that an enforcement mechanism is sound with respect to a policy P. It means that any state under the enforcement mechanism satisfies the policy P. And precision, we say that an enforcement mechanism is precise with respect to a policy P. It means that for a state that already satisfies P, then the enforcement mechanism does not change its behavior. Okay, so now we look at the answer of the first research question. Is there any sound and precise enforcement mechanism for TSNI? So if you remember the title of the talk, then yes, the answer is no. But now we will look at the process to achieve these results. So first we look at a simple setting. We consider a batch program from natural number to natural number, where all input number and output number are considered as confidential input. And so a batch program in this setting can be considered as a partial function from natural number to natural number. And now we define a policy called termination-sensitive policy, TS. And a program satisfies TS if it either converges on own input or diverges on own input. And we prove theorems that there is no sound and precise enforcement mechanism for TS. And an important part of the proof is a diagonal argument, which is similar to the argument of the proof that the set of own index of total program is undecidable. So from this theorem, we have the corollary. There is no sound and precise enforcement mechanism for TSNI for a program with I/O operation, because if there is a sound and precise enforcement mechanism for TSNI with I/O operation, then there is a sound and precise enforcement mechanism for TS in the simple setting, which is a contradiction. So I have just presented that. The idea of proving that there is no sound and precise enforcement mechanism for TSNI. And one important part of the proof is that there is no sound and precise enforcement mechanism for TS defined in the simple setting. So therefore, we have two important remarks here. The first remark is that the impossibility results can be generalized to other settings. For example, to other languages to other Turing-complete languages with other features. Because in such language, because we can prove that if there is a sound and precise enforcement mechanism for TSNI, then there will be a sound and precise enforcement mechanism for TS, and which is a contradiction. And similarly, the impossibility results can also be generalized to other policies having the similar requirement about termination behavior. For example, these classification policies described in a journal article by Bach et al. In 2011. Okay, so I have just presented the impossibility result. So now we look at the second research question. Which policies enforce soundly and precisely by secure multi-execution? So we have a policy called indirect termination-sensitive non-interference, ITS&I. And difference from termination-sensitive non-interference, then this policy assumes that a public observer cannot know whether there is a step of execution. So therefore, the observer can only infer indirectly the termination of execution. For example, if this observer does not see any event visible to him, then he may infer that, he can infer that the execution terminates. So we prove that SME with a fair scheduler, that means that all local execution have a chance to execute, then it can enforce soundly and precisely ITS and I. And SME with a low prior scheduler as presented in 2010, then it's only enforce soundly ITS and I when the security lattice is totally ordered. And SME with a low prior scheduler actually does not enforce precisely ITS and I. Okay, so now is the summary of my talk. So first, so we discovered that SME with a low prior scheduler does not enforce soundly and soundly termination-sensitive non-interference TS and I. And we proved that there is no sound and precise enforcement mechanism for termination-sensitive policies. A policy defined in a simple setting requires that program either converges on own input or diverges on own input. And as a consequence, there is no sound and precise enforcement mechanism for termination-sensitive non-interference. And SME with a fair scheduler enforces soundly and precisely a policy called indirect termination-sensitive non-interference, which is subtly different from termination-sensitive non-interference. And thank you for your attention.
All right, questions? No questions, really? All right, I have a question.
Yeah.
Maybe somebody can walk up to a microphone in the meantime. All right, what about progress-sensitive non-interference? So there are a bunch of papers looking at progress-sensitive non-interference. Are they all wrong?
So you're talking about progressive sensitive non-interference. So I think that the basic idea behind progressive sensitive non-interference is actually similar to the idea behind our policies called indirect termination-sensitive non-interference. Just there's some minor technical difference that because their definition may define on finite traces. For us, we define on infinite traces. Yeah.
Fair enough. Thanks. Any questions? Any other questions? No? I guess you're all hungry. All right. Well, with that, let's thank him and